Thank you for the invite from the Royal Aeronautical Society to let us come and have a talk to you about the program. We appreciate that. I was here earlier in the year with my wife Glenda, who's up the back there. She's a sand groper, so I'm a Queenslander. And we were here earlier in the year and spoke with the Royal Aero Club at Jandakot, a slightly different presentation. I did that solo, but I do appreciate the ability to come along and talk more about the project that we really do believe is the right aircraft now that Australia's procured. I'll be talking to you part way through, and Tom will do a lot of the talking, because apart from being the Executive Vice President and General Manager of the F-35, he was a former President of Lockheed Martin Aeronautics, and he was also the Exec VP and the Program Manager for the F-22 Raptor. So he's run the top two projects in the US Department of Defense for fifth generation fighter aircraft. So there's not much that Tom doesn't know about the aircraft. Just going to myself a bit, as I said, Glenda and I live in the Fraser Coast in Queensland, Maryborough-Harvey Bay district near Fraser Island. Glenda's a Starcevich and comes from WA, and there's about 5,000 of them living around. A lot of farmers on the wheat belt, and her Uncle Tom was the VC winner in World War II here, from here. As Harry mentioned, Betsy Clark. I won't tell you her age, but her category group in the Ironman was the 70 to 74-year-old, and she ran that. She started at 8:30 on Sunday morning doing a 4-kilometre swim, they do, and then she rode 190 I think it is, kilometres on the bike, and then they finished with a marathon. She didn't quite finish, but for somebody that age, and what she did was phenomenal. She finished her exercise, so she started at 8:30 in the morning and finished at 9 o'clock at night, so she was actively swimming, running or riding in that time. She's travelling at the moment, going back to Queensland. Betsy's an American. She's worked a lot for the Department of Defence over there. She's a colleague of mine, and when I was in Defence, I had her come out under contract and work with me, and together we've worked for probably about 20 years on various projects. I'm retired now from Department of Defence. I did 20 years in the Air Force, 7 years with the Fleet Arm after I joined Department of Defence, mainly in the introduction of the S-70B2 helicopter. And then, interestingly, I went and worked for Bombardier for a little while, building electric trains, which now run up and down here to Mandurah. So those trains that you guys ride in are the ones that I built in Maryborough. And also I do some consultancy work for Defence, and I'm right in the middle of a review at the moment on our air warfare destroyers. So that's our background. We've authored the book with another person involved, who's a gentleman by the name of David Poyer. David's the most notable maritime writer in the US, and we're all, three of us were engineers and pilots and technical speak. So we had David work with us to tailor the book down a bit to the aviation enthusiast. If anybody's interested, there's a couple for sale out the front there. They are signed, they're first editions, and the 4 authors' signatures are in the front of the book. Okay, most of you are probably aware the F-35 is the latest Royal Australian Air Force acquired Joint Strike Fighter. We now have nearly the full complement, and it's a stealth 5th generation aircraft. What does that mean? It's multi-role. It's very difficult to see on radar because of the stealth technology that's been embedded into it. It replaces the functions of a lot of different aircraft in its multi-role capability, and we'll show you some of that as we go through. I'm going to be talking about the F-35 aircraft and its technology, and Tom will be talking about the program and the management development of the program some of the challenges that we faced and he faced as they went through the development. The contract was started in 2001. The first aircraft went into operational service with the US Marines in 2015. So that gives you a bit of an idea of the time span of development. So I'll just start moving through. The photo you see on the lead slide here is the 1000th aircraft. So in that time that it's being developed from 2001, there's now over 1,060 and probably more, because there's a website I'll show you at the end you can go to, and it shows these monthly statistics for the program, and you'll probably find that quite interesting. It's got a lot of other detail there and a lot of photographs. And so Australia has acquired 72 of these, but there's not just one aircraft, there's multiple variants of the aircraft, and we'll explain that now. We've already talked about the three of us that are involved in writing the book. Betsy and I started that, and I was intending to do a case study for program management, and we interviewed Tom in his home in Alpharetta in Georgia, which is where he is now, and it's very early morning over there, by the way, about 6 a.m. And Tom was a font of all knowledge for us doing the interviews about the program, and he said, you know, he offered to help with the book, and we said, well, let's join together, and we did. And so that changed the nature of what we were intending to do from a case study into a book about the program. And he's had a database of heaps of information that no one else could have. The book, by the way, is based on interviews we had based on our own experience and knowledge with the program, as well as over 100 senior executives and managers and chief engineers from the program. So it's basically their story in the book, and all of those people did interviews of over an hour with us, and we recorded those, got their permission to publish what's in the book. And so it's quite an enlightening story. The challenges they faced in a transformational technology of this aircraft is quite phenomenal. The book is sitting out on the table out the front there. I won't say much more about that. We launched that in 2023. Tom and I went to the Royal International Air Tattoo in RAAF Airport in England, and we launched it there. So at this stage, just to say what the aircraft does is fundamentally it replaces these particular aircraft you see here. So the F-35 variants, and there are three, and we'll talk about why they're variant and what's different about them. The roles that they perform are what these aircraft in current aircraft are doing right now. So three variants of the F-35 replace this lot of aircraft you see here. Anything from the A-10, the F-16s, F-18s, F-111s, and so on. So when you think about it, the development of the F-35, while very expensive, if you had to replace all of these individually, then the cost, I would suggest, would be pretty much the same, if not more. I'm going to hand over to Tom now, and he's going to talk about the next couple of slides. Tom, are you with me?
As Adrian said, if you had to replace all those, it would be quite an accomplishment to integrate all those requirements. And the requirements were written specific for each service's application. So the Air Force wanted 9 Gs, they wanted an internal machine gun. The Marine Corps wanted to be able to take off and land, to land vertically, take off if you didn't have much storage on. The Navy wanted to be able to operate off of ships with catapults and arresting gear. So those requirements drove 3 different airplanes that, to the outside observer, looked different. In some respects, to the pilot, if I put all 3 of them in their conference room with you right now and you got in them into the cockpit, you wouldn't know which one you were in. They're all the same. So this first slide is, we started with the X program, where Lockheed at the time, we weren't Lockheed Martin yet, and Boeing were down selected from 3 to build X airplanes, which were demonstrators. And the first picture is the X-32. And you may wonder why there's an X-32 and an X-35 and what happened to 33 and 34. It turns out that the X airplanes are numbered in sequence, and in between the Harrier development program, Harrier replacement program, which was called STOVL, Advanced Short Takeoff and Vertical Landing Program, and the Joint Strike Fighter, there were two other projects. One was the single stage to orbit aircraft, and then the escape vehicle for that craft was called the X-34. So the space in between was taken up by two other aircraft. This picture is important because it shows you the difference in the two design philosophies. The X-32 came out of the STOVL and was well underway with Boeing and McDonnell Douglas, and it was to replace the Harrier. To do that, it was using the direct lift concept, which means the engine has to be essentially over the center of gravity of the airplane, which pulls the engine up into the middle of the aircraft. That's why it looks kind of chunky in the middle. There were a lot of compromises that were driven by that design, but that was the design that the Boeing team brought forward for the Joint Strike Fighter competition. A couple of things that I'll point out. With the engine up forward, it makes the airplane big in the front, and when you want to go Mach 1.6, which was a requirement for the airplane, you have to slenderize the airplane going back to reduce what's called the boat tail drag. When you do that, it makes it difficult to remove and replace the engine out the back of the airplane. So you basically have to remove the engine by dropping it down to the ground vertically from where it rests in the airplane. That drives a compromise in the weapons bays, because the weapons bays are essentially under the engine. Now you've got to move the weapon bays kind of up on the side. The other issue is that the one part of the airplane that you really want to hide is the engine face, because any radar can look at the front of an airplane and count the blades and tell you, basically identify the airplane if they can see the engine. You can see with the engine that close, it's difficult to hide the engine face. So there were compromises to this design, and I think that's what drove the selection process to the Lockheed Martin candidate. If you go to the next slide, please, Adrian, you can see again the airplane taxiing out on the runway. The other design feature that Boeing was trying to drive was to minimize the cost of manufacturing. And if you look at that wing, it was a single piece wing, which with basically the body of the airplane hanging underneath the wing. That could drive a slightly lighter weight airplane. It could drive some efficiencies in manufacturing, but it's a challenge to maintain in the field because any damage to the wing is basically an entire wing replacement. So those are some of the compromises on the X-32. On the next slide, you see the X-35, which is now the F-35A. And the basic design for that one was to move the engine back where it is on a normal airplane, toward the back of the airplane, and assist the engine with a lift fan that goes right behind the cockpit. If you've seen an X-35B, and there's been a number of them operating down in Australia, primarily up in the Darwin area, I believe, with the Marine Corps, it looks a little bit different. It basically gives you 2 points of lift. The tailpipe can swing down. The lift fan brings cool air in through the top of the airplane, and you lift the airplane up on two essential lift posts. There's also hot air that's brought out to the wings to give it roll control, particularly if you have the issue of asymmetric stores, where you have stores stuck on one wing or in one weapons bay. You have to balance the airplane, and the roll axis, it allows you to do that. But a much more conventional looking airplane, if you put your face up to the inlet and look directly in it, you can't see the engine at all. It goes around a curved surface. So it hides the engine, which is very important in stealth. The next slide. I'll mention one thing on the slide that shows the airplane from the top view. The Air Force was the only service that required an embedded gun. This is the version that the Australian Air Force uses. You can see the bump on the left wing going forward. That is the machine gun that goes in that airplane. The other two airplanes carry a gun, but it was not required to be embedded in the airplane. It's carried in a stealthy pod on the center line of the airplane underneath. Still allows you to use both of the weapons bays and have the gun, but not carried internal. Over to you, Adrian.
So Tom's just spoken about, we call that the CTOL, Conventional Takeoff on Land. So Air Forces around the world, it's predominantly the biggest number of aircraft variants that are built is the CTOL model. I don't know how many exactly, but there are the majority of CTOLs. Then there's the B model, which is the STOVL, and then there's a carrier version, and I'll show you what they are as we go through here. So Tom's covered the CTOL. That's a Gatling gun, a 4-barrel, 25mm gun. It fires 3,300 rounds per minute and carries about 180 rounds. So they don't have much in the way of armament. I think the A10 carries hundreds and hundreds of rounds that are replaced. But today, strafing is not a big activity. Today, it's guided missiles and guided armament, laser-guided bombs. So strafing with a cannon is not a big deal anymore in warfighting. This is the performance figures relating to the F-35 CTOL, or the Australian version. Tom's already mentioned a couple of aspects here, and Tom, I'll just get you when I've finished on this one to just mention a couple of those variations. But here you can see the top speed is Mach 1.6. There are fighters that can fly faster than that, but the one thing you've got to remember is that an F-35 carries its armament and its weapons in a weapon bay. And you'll see a photo shortly of the weapon bay. So there's no external stores normally carried if it's in stealth mode. They're inside the aircraft and they're hidden from radar. If you took an F-18 and with its bombs and rockets on the pylons, it'd be very visible. So it's all part of the stealth. And it can do 1.6. If you take those 4th gen aircraft with the armament on their pylons on their wings, they wouldn't do that sort of speed, so it's not really an issue. It can carry about 18,000 pounds of weapons inside, so that's bombs and rockets, and you'll see a photograph of some of that shortly. What else is up there? 9G. It can pull 9G, which is pretty high. You can see the thrust. It's a Pratt & Whitney F-135 engine. It gives about 43,000 or 40 to 43,000 pounds of max power. And that engine, I think Tom replaced, is roughly about the same power as the 2 engines on an F-18, is that correct?
Yes, that's correct.
So out of the 1 engine, they can get the power of equivalent of 2. Apparently, I think Tom mentions to me that when they were looking at whether they go 1 engine or 2 engine, they looked at the statistics of engine-related failures, and they found that the rates didn't vary much between a single engine or a twin engine. So why have twin engines when you don't get any particular benefit? In history, they have not had to rely on the second engine frequently. You got any more to add to that, Tom?
That was driven by life cycle costs primarily. It's much cheaper over the life of a huge fleet of airplanes like this to have a single engine rather than 2. There's some slight differences in the engine. This is the F-35A engine. The thrust levels are about the same, but in the B, you augment that with the lift fan, and with the C, you have one that's tailored for operation on a big aircraft carrier flight deck. If I can run down a couple of these other ones, and I'll just point out the differences in these. All 3 of the airplanes are Mach 1.6. It's not that they can't go faster, it's just that's the limit of the airplane from a design standpoint. And they are well within that. One thing that sets them apart from a conventional airplane like an F-16 or an F-18 is the weapons, as Adrian said, are carried internal, which means it's still a Mach 1.6 airplane with weapons. If you put weapons on an F-18 or an F-16, it becomes subsonic just because of the drag of the weapons. We don't have that same issue. It also maintains its G capability with weapons internal. The wingspan on the A is 35 feet, is slightly less on the B, slightly more on the C. And the wing is where most of the fuel is, although the fuel is in every available space on the airplane. So the fuel quantity that you see here for the A is the middle of the pack. The B is less because we replace the fuel tank with the lift fan, and the C is more because the wing and flight control surfaces are larger, and that's driven to slow the airplane down for landing on the ship. So there's more fuel in the C. let's see, on the G rating was driven by what the services asked for. The services asked for 9 Gs on the A airplane, which is primarily the Air Force. The Marine Corps wanted a 7G airplane, so that's the B model, and the Navy traditionally flies with a 7.5G airplane. That's what the F-18 is stressed for, and that's the amount for the C model. That's an important factor because that drives the amount of structural weight that the airplane is required to carry to pull those kind of loads on the airplane. Engine designations are all the F-135, although the dash number is slightly different for the 3 of them. We'll cover that more in a second, in a few minutes. So, max afterburner 40,000. As Adrian said, it's actually 43, but we labeled it at 40. If you look at an F-22, to show you how the technology changed over the 10 years difference of that airplane, the F-22 uses the F-119, which is the baseline for this engine. It's still a 25,000 pound dry thrust airplane, 35,000 pound maximum afterburner. F-35 takes that up to 40,000 plus. So the technology is primarily in the ability to go into the high thrust region in terms of temperature. Back to you, Adrian.
That engine, by the way, is accompanied by the stuff that we deal with in my profession as a million lines of code in the engine control system, which is bolted onto the side of that engine. The B model, the STOVL, short takeoff, vertical land. So here you've got an aircraft that'll fly up to you doing Mach 1.6 and then stop mid-air and then lower itself down. It's quite amazing. You can see the nozzle there on the tailpipe pointing straight down, and I'll show you an image of the engine internal in a minute inside the aircraft fuselage. But the door above the canopy is open for the big fan. That's a Rolls-Royce fan, I believe. That fan generates the thrust in cold air, which is better than the Harrier or the alternative X-32, where they only had hot air. And if you ingest the hot air into the intake, you can cause loss of power. And I think the Harriers and the AV-8Bs in the US had problems with that. Whereas in this particular aircraft now, that air up the front is cold air. You'll see there's a set of doors behind the fan over the lift fan, and that's opening more air to allow more air into the intake of the main engine. I'm not sure, Tom, what was stopping? Why did they need that?
The engine, when airplane comes down to a stop, basically hover is not pulling enough air through the 2 inlets because there's no forward speed on the airplane. So we had to augment that air into the main engine. So those green, are you on the green door slide, Adrian? I'm not sure which slide you're on.
I'll go to the green. I'm now on the image with the green doors.
Okay, yeah, it's easier to see it on this image. The green doors open up to allow more air to come into the main engine. The big 57 Chevy hood door that you see on the previous picture allows air to come in through the lift fan. One of the interesting test sequences we had to do was to fly without the lift fan turning with that big door open. You can imagine what that does as a speed brake, and the airplane was not able to maintain altitude. It was slowly descending to keep going forward at 100%. But when the airplane's in the hover, the main engine is at about 97% thrust, dry thrust. So there's about 3% margin that you can use to maneuver the airplane up or down. You see the blue center piece there, the wing carry-through structure. Right in front of that are the 2 what's called lift posts, where the fan air is pulled out and ducted out to the wings to allow you to have some roll control while the airplane's in the hover or slow speed. So the airplane flies that they're doing now landings with slight forward motion. If the shipboard use can generate some wind over deck, the airplane can approach at a slow speed, and that allows you to bring back a lot more weight in terms of fuel and weapons if you have weapons on board.
Tom, what's the drive shaft revs when it's in that 97%? How fast is that spinning?
The shaft, this is an excellent point, Adrian. The shaft of the main engine comes out and it's turning at about 26,000 RPM. The lift fan that it touches into is essentially shut down and not spinning at all when they go into the STOVL mode. If you think of a turboprop airplane, it's the same concept. The shaft comes out of the main engine driven by the turbine, and it turns propeller in the vertical plane. We had to convert that energy to turn a lift fan in the horizontal plane. It's a two-stage counter-rotating fan to get rid of the Coriolis effect on turning the airplane right or left. And you basically clutch that rapidly spinning shaft into the lift fan. It then spins itself up as the airplane's slowing down. The door opens, the airplane converts to a hover.
Okay, thanks. So 26,000 RPM to a clutch from standing still. Then have the carrier version, the CV or the C model. I try to identify, when you look at them, what can you see? On the CTOL, you'll see that bump where the Gatling gun is on the wing, so you'll know it's a CTOL. On the carrier version, they have twin nose wheels, and they don't have those on the other. So for carrier landing, you can't see it very clearly there, but there are twin nose wheels on it. Tom will talk a little bit later about what the flight control system has meant to this with the magic carpet ride.
Yeah, the only thing I would add to that, Adrian, is you mentioned the two nose wheels. That's primarily so if you blow a tire on the catapult stroke, you don't have the catastrophic effect of the airplane dropping down on the nose gear structure. The other interesting thing about the Navy airplane is the wings fold for parking on the flight deck. And one of the real challenges was running the fiber optic cable through the wing fold to activate the sensors that are embedded in leading and trailing edge surfaces of the airplane. The other one that was especially difficult was the tail hook. If you think about it, the tail hook has to be hidden for stealth reasons, and it may have to be used 3 or 4 times in a single day. So you have to be able to raise and lower the tail hook without impacting the stealth features. What that does is it drives the tail hook to be much shorter than a traditional airplane. If you look at an F-18, its tail hook extends well beyond the engine area. Hiding the tail hook turned out to be a significant challenge in physics, because as the main gear, you can sort of see it here, as the main gear rides over the cable, it creates a wave in the cable, and the hook has a tendency to miss the cable coming behind it. So we had to put a lot of effort into designing that whole end of the airplane, which tends to not come up as a major design criteria for most people that think about airplanes, but it was one of the more difficult things to do, is to maintain stealth when the airplane is not using the hook, but allow the hook to be used multiple times in a day. The Air Force airplane also has a tail hook, but it's an emergency feature. If you're having a brake issue or some kind of a problem where you're going to overrun the runway, you might drop your hook. You might do that once or twice in the life of the airplane. This one you do it multiple times every day, so it drives an entirely different design problem.
This is the Pratt & Whitney 135. It's a fairly large engine. It is in 3 pieces. The intake area, the turbine, and the tail nozzle area. It can be transported like that, but if you have a look, I think the specified hours for this were similar to the life of the aircraft, Tom, were they not? So the aircraft is, I may be corrected, but I think it's around 8,000 hours, and the life of the motor is about 8,000 hours. So if your reliability was met, then they may not do an engine change in the life of the aircraft, which is pretty amazing. You can see some of the Pratt & Whitney statistics there on the side. The pull-out rate of the engine, you don't have to have maintenance. You don't have to do engine runs and tune them like we used to do on the F-111s. The change out is quite low. You can see it's 93% less than the removals on 4th gen aircraft. So it's a pretty interesting engine, and they're upgrading that at the moment, I think. Tom, they're putting in features to give more electrical power to the Block 4 upgrade.
Right, there's a significant upgrade going on to to carry the next generation of weapons, including directed energy type weapons. And to do that, you have to generate more power from the engine, not necessarily more thrust, which is what the pilots like, but more power to drive the electrical energy that goes into some of the newer weapons that are being developed. So the engine is going through an upgrade at the same time the airplane is going through an upgrade.
Okay, we're going to the next slide. Tom, you might want to talk about this one. The engine test stand, Pratt.
Yeah, this is the engine test stand at the Research and Development Facility in West Palm Beach that Pratt Whitney uses. And I was there, they ran this for the first time. You can see they have to attach the engine up in the air onto a stand because the lift fan and the nozzle both rotate down. When they ran this the first time in the STOVL mode, and this is in the normal up and away afterburning mode, the airplane does not use the afterburner to hover. Obviously, there have been some short takeoff vertical landing airplanes in the past that did do that, but it creates so much damage to the ground around it that was not something that we did. So the engine can only be in military thrust when it's in the hover mode. At this point in time, in this picture, it's in the afterburning mode. But the first time they ran it in the STOVL mode, it actually pulled this structure up out of the concrete and created cracks in the ground that they had to go back and repair because they were estimating what the thrust would be. It turned out to be a little bit more than they estimated when they went to full power. So it was quite, if you can picture yourself being a pilot and walking out and strapping in, and just sitting on top of that without the airplane around it, it's a pretty frightening thought.
So in the next slide we have the family, the three variants. The top left is the STOVL, conventional takeoff and land, the Air Force version, the Australian one that we have. On the bottom you'll see the STOVL. You can see the lift fan there behind the cockpit, and the engine and all of the variants at the rear of the aircraft. And you can see the larger wings there on the CV. But when you look at the aircraft, it's very hard to tell the difference from a distance. And as Tom said, if you're sat in the cockpit, you don't know which one you're in. I think might be one more control for a STOVL somewhere in the cockpit. We'll show you an image of the cockpit shortly. You can see. Go ahead, Tom.
Yeah, let me add. It's interesting that if you sat in the cockpit of the B model, there's a switch about 1 inch by 1 inch by 1 inch down on the left-hand side of the front panel that says STOVL on it. And when you want to go into the STOVL mode, you push that button and the airplane starts reconfiguring itself as it slows down. That same 1 by 1 switch in the CV or the STOVL airplane says hook. That's the difference. But everything else in the cockpit is exactly the same.
Good, thanks. The other things here, you can see the STOVL has boom refueling, as distinct from hose and drogue for the other variants. They can, with the boom refueling, it's a lot faster. They can fuel our tankers, the Airbus tankers that we have, and our Air Force has the boom and the hose and drogue capability. What else is there? You'll see the cannon on the STOVL. The nozzle that pivots down on the B model.
One of the things you can see there is the difference in the size of the wing on the CV, on the C model. And we looked at a number of different ways to slow the airplane down. There's a direct correlation between landing speed and accident rates on a flight deck of a carrier. And the simplest way to do it without some kind of special blown flaps or some kind of a special lift system was to have a bigger wing. So that drove us to a bigger wing on the airplane. Most of the engineers who are aesthetically inclined believe that that's the prettiest of the airplanes in terms of the wing size and its relationship to the fuselage. It's driven primarily by the need to slow the airplane down for landing on a carrier, though.
The next one we see here is the cockpit. You'll notice there's no analog instruments in the cockpit. They have a screen which would be a quarter of the size of the one of Tom's in there now. Touch screen, so the pilot, when he wants to see any information, he just has to touch the screen in a particular area and it'll bring up the information that he needs. That's sort of redundant because the helmet, and Tom will talk about the helmet shortly, projects in his face the critical information that he needs in his flight, and also contact information is projected in the helmet itself. The helmets for this, I don't know what they cost today, but when I was involved with them, they were somewhere in the order of nearly $500,000 each for a helmet. The touch, let's call the panoramic cockpit display, you can see there with the attitude heading reference. There are 11 segments or so on that screen you can bring up and have 11 different types of information displayed. You'll also notice there's no control column in the centre. They fly this aircraft with joysticks, one on each side. Tom, you got anything to say about that?
This is where the software really comes into play. To simplify the task for a single pilot, the software integrates all the sensors. So on a 4-gen airplane, you would see a radar scope, electronic warfare scope, different scopes, and some analog information. This one, you see the big screen, and you basically watch the movie. You don't know what sensor is providing the data. It's all being fully integrated through the software, and the pilot is really watching the world around them as opposed to looking for any indication from a different display. That's where the lines of code come in. I think Adrian mentioned earlier, if you look at an F-22, there's about 2,000 lines of code in the airplane. If you look at an F-35, there's about 9,000. There's about 2,000 in the engine alone. So the amount of software that we're able to generate and manage inside the airplane has grown by a factor of about 5 in the 10 years between the design freezes on the airplane. The other thing you can notice in this picture is that the canopy opens forward. A lot of people say, why do you do that? It has nothing to do with actually the operation of the airplane. It has to do with the life cycle cost. If I open the canopy forward, I can remove and replace the ejection seat, which requires replacing pyrotechnics and things like that on a more regular basis than the airplane. It turned out that when they analyzed the maintenance man hours per flight hour, the removal and replacement and realignment of the canopy was more than the hours it took to remove and replace the ejection seat. So if we could eliminate that act from the maintainer standpoint, we could drive down the hours required to maintain the airplane.
Tom, just to correct you there, you were saying thousands of lines, it's millions of lines of code. So
yeah, I'm sorry. Yes.
9 million lines of code to operate the avionics and the weapon systems. What Tom was talking about is what we call data fusion. In the aircraft, there's a number of sensors. Some of them you'll be aware. There's infrared, there's radar, there's electronic warfare systems that are sensing information. In a conventional 4-gen aircraft, the pilot has to look at those different displays and determine what the threats are around him. On the F-35, it tells him. He doesn't have to do that. He can concentrate on flying, and the system will identify the threats which are hostile and project that into his helmet, and he'll see that in space where they are projected in his eyes. And so what happens is they fuse all the data from the different sensors, which makes it and concludes what's threat, what's hostile, etc. And they do that, what we call own-ship fusion, but they also bring the data from all his partner aircraft in the wolf pack that normally they'd fly with something like 4 aircraft. And so they fuse the data in their own aircraft, but each aircraft sends their data to each other aircraft. So they're not just fusing the one set of data, they're fusing the data from all the aircraft that are flying in the wolf pack. And they might be separated by quite a bit of distance, so they can see the whole theatre of operation basically, whereas normally you would only see what your sensors can see. And so that's a major transformational capability that's in this aircraft. 3-dimensional positioning and everything is much more accurate due to the data fusion, multi-ship data fusion. This is a video just going through the 3 models. That's the STOVL version just taking off, and he's going to launch a rocket soon. You'll see the weapon bay door come down, and there goes the missile. That missile, by the way, was mounted on the inside of the door. That's the STOVL. You can see the lift fan door opening there. You see his nozzle swinging, and away he goes in a very short run to take off. and here he comes back. They fly in normally beside the aircraft. This is the carrier version. Conventional catapult and arrestor system. The Marines tend to operate the STOVLs, and a lot of their ships don't have catapults. They're amphibious attack ships. They're an expeditionary force. They take them to where they might have to operate around the world and can land where they have to, even if it's on a highway. Over to you, Tom, for the next bunch of slides.
This is, it's hard to give these presentations sometimes to non-technically, non-military oriented audience. So we described it as an archipelago, which stands for islands in a common sea. And when you have a number of countries that are concerned about replacing their aging aircraft, most of these countries fly U.S. aircraft. The inventories are aging at about the same rate. The STOVL probably faster than the others. And so the replacement of that fleet of airplanes historically has been to build it for the U.S. and then sell it to international operators later. In this case, the idea was to bring all the countries, bring the core countries, 9 of them in the beginning, together to do the development, to integrate their requirements early on. A number of the primary countries had their own weapons that need to be integrated. So we started out as a 9-partner country, and you can see the flags there. U.S. and U.K. were already teamed on a program called STOVL to replace the Harrier. That program was canceled, and its requirement was rolled into the Joint Strike Fighter, which is what resulted in the B model. You have Italy and Netherlands, the next two, that came in at a higher investment rate than the rest of the countries after that, at about $1 billion apiece for the development. Then you have Turkey, Canada, Australia, Denmark, and Norway, tending to be either F-18 or F-16 operators. That was the core group in the beginning, and our requirement was to integrate those into the team. The Joint Program Office in Washington was staffed by officers from all of their air forces. The industrial participation was a key factor. I spent a lot of time in Australia trying to find companies that could do work on the program. It requires a much greater fine ability to manufacture fine detail for stealth reasons, and I will cover more about that later. Over the course of time, the Turkish nation decided to buy the Russian S-400 system, air defense system, and they were then excluded from the program. So out of the core group of 9, today there are 8. Then there were 2 other countries, flags below that, Israel and Singapore, that came in and would buy the airplanes through the normal foreign military sales process. They wouldn't be involved in the design and development necessarily. They were a separate category. In the end, Israel wound up, as most of you probably know, being the first to take the airplane into combat. We can talk a little bit about some of their lessons learned later. And I think if you click it, I can't see the slides, but if you click it, I think another row of flags will come up. But these are the countries that have come in since the airplane was designed and developed. And if I just run across the bottom, there's Japan, South Korea, Republic of Korea, Belgium, Germany, Poland, Switzerland, Czech Republic, Norway, Finland, and Greece. And since this chart was made, Romania, I understand, has also joined. So there's about 20 countries today that are somehow involved in the F-35. When Russia invaded Ukraine, that was kind of a wake-up call, and a number of the countries around the Canadian Arc, Northern Europe, jumped into the program. So a large number of countries, most of them are buying the A model or the CTOL model. Some that operate ships, as an example, Italy and the UK are buying the B model. Italy is actually buying both the A and the B, the A for the Air Force and the B for the Navy. So that's the archipelago as we define it today. The next chart, if you would, Adrian, is how do you define what the operational benefit of this is? If you think about conflicts that we've been in, whether they're warfighting or peacekeeping, are not done by a single service and are not done by a single nation. We fly and fight as coalitions and as joint operations. Historically, that's been difficult because the airplanes are all different. even though they maybe a number of them flying F-16s, the systems in the F-16s are different because they were bought through a system that allowed the acquiring country to put their own equipment into the airplane. So now all of a sudden you have the coalition of allies, all three U.S. services, all sitting in the same airplane. You can join the fight from a ship, you can join the fight from an international partners country. That changes the whole paradigm of how you fly and fight as coalitions. So again, the benefits are kind of shown on the right there. There are economies of scale. Yes, the development program was longer than anticipated and took more dollars than was anticipated. None of those additional dollars went back to the partners, however. The acquisition of the airplane is actually less expensive than if you were going to buy one of the 410 airplanes off the production line today. So there are economies of scale. There are life cycle benefits to having the fleet. You've seen some of those on your C-17s and things like that, where you can fly a C-17 into another base and get parts for it because they're the same airplane. There are shared investments going forward. All of the fleet will get upgraded as a group, and the international allies are allowed to bring their requirements into that process of getting their requirements and their weapons integrated into the airplane. It's interesting when you have to fight the cost story every time you talk to somebody, which I had to do for 13 years. If you look at the way the costs were estimated on the F-35, they were to estimate the entire production run, 40-year production run, 3,500 airplanes as a baseline, life cycle costs over the operating life of those airplanes. When you added all that up, it came to something over $1 trillion. That's 40 years of operating a fleet of 4,000 airplanes. If you put that same algorithm onto an F-18 and assume the same numbers, it's about 4 times that. So that's where the moniker $1 trillion jet came from. It's not $1 trillion until you've finished, flying the airplanes over their life cycles. So that was one of the cost problems we had to fight as we went. Next chart. If you look at the two countries after the UK, which were the Netherlands and Italy, those two countries were given the option to do a little bit more than the other partners. One was they could buy operational test jets. The Dutch decided to do that. They bought 2 operational test jets. We took them out to Edwards. They were part of the integrated test team out there. This is Colonel Burgess Smith, who was the leader of that team. They were very efficient. All of their enlisted folks were trained across all the disciplines, which became a model for training the enlisted supporters for the airplane going forward. But they actually bought 2 test airplanes. The only other country to buy a test airplane to date has been Israel. They have their own test airplane in Israel, but because they integrate a different suite of electronic warfare type equipment into it. If you look at the next chart, title says another island in our common sea. But this is a facility in Cameri, Italy, about halfway between Milan and Turin. The Italians chose not to buy any test jets. They chose instead to set up a production facility where they could build their airplanes and some of the Dutch airplanes. In return for that, the Dutch would do the overhaul on the Italian engines. Some horse trading going on there on how they do that. But this facility is a clone of the Fort Worth facility. They assemble the wing in this facility, and they build the F-35 at about 4 a month, 48 a year, compared to the 160 a year that's being built in Fort Worth. So it's a low-rate production operation. The real intent is to make it the depot for European aircraft. For anybody that has an airplane in Europe, rather than send it back to the States, they can do the depot in this facility. So their investment went a different way, but it's an important facility that exists on the European continent. The next chart, probably the most challenging. The international partners tend to go with the flow. The services fight for budgets inside the U.S. budgeting system, particularly between the Navy and the Marine Corps. And one of the real challenging parts of the project was keeping all 3 of the services involved and happy with the way their particular variant was going in the development. And the next chart, Adrian. I wanted to put the pilots in here because Testing the airplane is always a challenge. You can see the 4 guys on the upper picture, and then across the bottom is the integrated testing. The guys in blue are Lockheed pilots, the guys in green are military pilots. The F-35 was the most tested airplane in the history of aircraft, primarily because there was 3 of them. We also had to take all 3 variants through 4 life cycles of structural tests. Those were articles that never flew, but were built exactly to the standards of the aircraft. It's a dangerous job, but it's also a lot of fun and a great job. Pilots like to do it. A bit sobering if you look at the lower picture. 3 of the gents in green were killed since this picture was taken. It had nothing to do with the F-35. They were also stunt pilots in their free time and flying other aircraft. But it is a dangerous job. We never lost an airplane, have not lost an airplane in test, which is unusual for an airplane that goes through this amount of testing. And most of I can't think of any accidents that have been attributed so far to the airplane. There have been a couple of accidents related to pilot error and other issues. But best seat in the house is the way they did describe their own job. And just to show you how nothing's done in secret, a friend of my daughter's was walking down the street in New York the day we did the first vertical landing at Patuxent River Test Center, and it was being filmed, and this is the Jumbotron on Times Square. So it's pretty hard to do testing in secret anymore, a lot of visibility. The next chart is what I call the miracle of the loaves and the fishes. We had one airplane, relatively small airplane. We had 9 partner countries, and all of them thought they should be building 51% of the airplane. So we had to go through quite a process of getting, first of all, identifying companies that could do the job, and if they couldn't, try to get them to the point where they could. And you can see how the airplane's broken up by colors there. What's in yellow was essentially the components that Lockheed Martin did. And then we had to identify second sources that could also build those same parts. The blue is Northrop doing the center fuselage, and to give you a sense of how big that project is, there's about the same number of man hours in assembling the center fuselage alone as there are in an F-16. So you build these components separately in factories around the world. Those factories are kept within plus or minus 2 degrees Fahrenheit of each other to prevent any mismatches by the time we get them all together in final assembly. They all come into the final assembly line, and then they're put together. And one of the challenges we had was the design priority in the beginning was to reduce that final assembly time down to where we could have a moving production line and basically deliver one a day. We're delivering about 160 a year right now, which is about one every other day. And part of that was driven by the issue that I'll talk about in a minute, which was we had to change some of the structural arrangement to get rid of some of the weight in the airplane. The orange area is BAE Systems. And you can see where the other suppliers come into play. Several of the parts and pieces are done in Australia. The primary company in Australia is Morand Precision Engineering. They make an item called the engine trailer. I think there may be a picture of it later on coming up, but if you think about it, it's very much of a misnomer to call it a trailer. It's got something like 10,000 parts, and a single operator has to be able to move that engine around on a deck of a ship that's in a sea state of about 4. So it's quite a mechanical piece. But that was one of our major challenges, was set up the supply chain and get it operating around the world. It was all part of the government-to-government agreement that countries that participated would be allowed to compete for work on the airplane. As long as they can maintain best value, they could stay on the airplane, or else their work would be recompete. You see there Turkish Aerospace Industries, the third one down in the orange. They were the second source for the center body that, as a sub to Northrop. When Turkey was excluded from the program, their work had to be repositioned across the other partners, which is difficult to do. And I believe that some of the newer countries that are coming in, I think Germany's the main leader, will pick up that role eventually, but it had to be moved back into Northrop at the time. I want to give you just a little bit about some of the things that drove, you might not think about, that drove some of the technical challenges. And if you go to the one that says major SWAT structural change, SWAT stands for STOVL Weight Attack Team. If you think about it, there's not enough engineers in the world to design 3 airplanes simultaneously, and you also don't get the advantage if you do that to do lessons learned from one to the other. Our initial design sequence was, we'll build the A model first, that's the simplest, then we'll do the B model, because if you put a B on top of an A, the shadow on the ground is the same, it's essentially the same geometry. And then we'll do the C model last, because the Navy was not in a hurry to get their airplanes. But we got the A model done, and we built the first one. We're working on the B model, and we're finding out that because of our philosophy of decreasing the assembly time, we were driving weight into the B model. And at that point in time, we didn't have a B model, so in essence, you're weighing your drawings, as they say. And we had if you look at the top half of this picture, you can see where we were building the wing, and then the wing was going to lay down on top of the center fuselage, which was being built by Northrop in California, the wing being built by Lockheed in Fort Worth. When we did that, in order to have those structures sound, we had to have basically a bulkhead on both sides of that, what they call the bake joint. Well, that was driving weight, as you can imagine, into the total structure of the two once you got them together. And the 2 bulkheads were not really required once they were together. They were required when they were separate. So when we made this one change, you can sort of see at the bottom picture there, we basically took the weapons bays off and put those into the wing. When we made that one change, we saved about 600 pounds of structural weight. The rest of the weight, we got about 1,800 pounds of weight out of the airplane. If you think about that, that's about an 18-wheel truck, or an 18-wheeler. We got that amount of weight out of the overall structure of the airplane, made the airplane much more efficient. If you ask the pilots, they'll say all 3 of the airplanes benefited from the weight reduction, but it added about 18 months of engineering into the program. And we changed the sequence to do the B first, which is the hardest one, then do the A, then do the C. That change in sequence was very difficult for our suppliers, because we basically stopped building the A model while we finished the B model and then got them all up and running again. But there were probably 2,000 changes that were made. Adrian mentioned the 4-barrel Gatling gun. It started out as a 5-barrel Gatling gun. So there were changes like that were just driving ounces out of the airplane until we finally got it down to the point where the B model could meet all of its operational requirements. It was all driven by the B model. The B model is the one that's most weight sensitive because it has to be able to land vertically. Next chart, if you would, Adrian. It's just a picture. This is the first CTOL jet. We called it the first flight. It's being moved down the factory on a crane. But you can see the factory is fairly empty, and that's because we were going through the redesign and going to start with the B first. That's what we call AA1, moving from one position to the other. Down underneath it, you can see the engine down there, and you can see the trailer that goes on, just as an example. If you go to the next picture, this is what the factory looks like today. We can build any of the airplanes in any order that you want. If you look down that line, there's A's and B's all mixed up and C's all mixed up. But today's rate, the peak rate is about 160 a year, which if you think about 320 or so manufacturing days a year, that's an airplane every other manufacturing day rolling out of the factory. So it's also, this is the factory in Fort Worth. If you look at the factory in Italy, and there's a third final assembly line in Japan doing the Japanese airplanes. They're much smaller than this, obviously, because they're running at a much slower production rate. Adrian, do you want to add anything to that?
I've been there a number of times, and the reviews I did over a 5-year period. That is over a mile long, that production line facility. And that's air conditioned, as he said, within plus or minus 2 degrees for every factory that's producing parts. We've got to keep to, I think it's around 67 or something like that degrees. You can imagine a mile long building, and that's got to be air conditioned. That's in Fort Worth, Texas. That's pretty hot. I've come out of meetings there of an evening, 7 p.m, and it's still been 110 degrees Fahrenheit. and they've got to be cooled down in that mile-long building to 60-odd degrees. It's an eye-opening. That's been there, and the F-111 was produced on this line. F-16s were produced on this line as well. The Eagle's Nest now has moved, and they have a separate building to build the F-16s. I'm just going on, Tom. We've gone through our hour, so we're going to have to pick up the pace.
Okay.
So, you want to talk to the Catbird?
Yes, quickly, this is a Boeing 737 that was owned by Indonesian Airlines. It was a low-time airplane that we purchased. We had to get in the air with the software and all the sensors. If you look at the little graphic on the upper right, there's an actual cockpit, F-35 cockpit in the front. A pilot would get in. The pilot's not flying the 737. That's being flown by pilots at the front of the airplane. But behind him were 20 engineers looking at how to continue to develop the software to integrate all the avionics in it. This is the most heavily modified Boeing 737 in the world. All of the features on there, the forward canard and the aft canard, are all geometrically identical to the airplane. So we had to have a flying airplane to do the final tweaking of the software to when we get to the full fusion piece. The next chart shows you that aircraft as it's taxiing out, and you can see the F-35 radar on the front of it, and the little winglets that simulate the leading edge of the wing and the aft. There's sensors in all through the airplane, so they all had to be geometrically the same. Go to one more, and that's the other piece that was very challenging from a software perspective was the software to fly the airplane. Nothing to do with the sensors. The upper left corner is the Bach Harrier. It was flown at Boscombe Down in the UK to develop what we call the unified flight control system. If you sit in the airplane and you want to go up or down, normally you would pull back on a stick as a pilot. In a vertical landing airplane, your hands actually act differently whether you're going up and down or forward and aft. So you command thrust differently. We wanted, from a training perspective, for the pilots to be able to go from an A to a B to a C without special training. So we wanted your left hand to always be your motion forward or aft, and your right hand to always be your altitude control. But if you think about it, when you're in the STOVL hover, if you want to go up, you have to increase thrust. So without you knowing it, the control of the engine went from your left hand to your right hand. Intuitively, to the pilot, is natural. It's made the airplane extremely easy to fly, and pilots go from one to the other with no special training. But from a software standpoint, we had to move the control of the engine from one end to the other. If you look at the carrier-based airplane, again, we had the dynamic with the tail hook I mentioned. Today, the F-35 is so repeatable on landing that they're wearing out the 3-wire on the carrier, and there's a spot on the flight deck where the hook's hitting all the time. So the variable carrier landing was covered with this long acronym that's on the left. If you take the first letter of each word, it spells out magic carpet. F-18 incorporated the same flight control system today, so it's really made the landing aboard ship a much easier, much safer operation. The helmet, Adrian mentioned on the next slide, it doesn't look like your traditional crash helmet where you're just trying to protect your head. Everything is contained inside the helmet. All the information that you would normally see in the airplane can be brought up and projected on your helmet visor. There's cameras positioned on the outside of the airplane, so you're actually looking through the cameras and not through the airplane. As an example, if I come in to land on a flight deck in the STOVL airplane and I look down, I don't see my legs. I see the flight deck underneath the airplane. It was an interesting. The flight surgeons were afraid that it would be disorienting to the pilot, but it's turned to be quite different. This day or night, the pilot can display the images of what's going on his helmet. He can target through his helmet. It's an essential part of the mission system on the airplane. On the next slide is we also had to develop the ejection system. If you think about opening the pilot envelope, where the minimum weight for a pilot in fourth generation airplanes is about 150 pounds. Now we were going to take that down to 100 pounds. The upper end is about 230 pounds. If you talk about nude weight, then you have all your flight equipment on top of that. So we had to have an ejection system that wasn't going to hurt the small pilot, but would still get the big person out of the airplane without leaving them in. And if you think about the flight envelope of the airplane, very high speed ejections on a small pilot can cause obvious neck problems if you eject at very high speed. So a lot of work went into developing it. You can see on the sled, this is at the Martin Baker facility in the UK, it says CTOL CV. That's the common system that's in those two airplanes. The STOVL airplane is a little different because if it's in a hover close to the ground and there's one failure mode where the shaft could break, probably will never happen in the life of the airplane, but it's possible. The airplane tumbles so fast that a human can't react fast enough to eject. So it has an auto eject. If the airplane senses it's going to do that, it'll eject the pilot. So that system is a little bit different than the one you see here. So there's a different sled to test that. And then you can see the number of Martin Baker seats, the number of people that they've saved. I'm going a little bit fast now, but we'll leave some time for questions. The next picture shows the weapons bays. The airplane can carry multiple weapons inside those bays. And again, it keeps its speed capabilities as well as most of its G capabilities when those weapons are inside the airplane and not hanging on external pylons. This one shows the wingtip missile pylons. That's the way the Navy traditionally flies, with internal weapons in the bays, but a missile on each of its wingtips. Some compromise in stealth, but not much when you do that. And the next one just shows you, again, if you think about how long it takes to test an airplane, all three airplanes had to be tested for all the weapons that the airplane is meant to carry. And that basically shows the weapons that each airplane can carry. One of the biggest challenges on the next slide is taking the stealth to sea. If you think about an F-22 or B-2 or any of the stealthy type airplanes that the Air Force flies, they're maintained in humidity-controlled hangars. You don't exactly have that when you go to sea on a ship. And you're open to the salt air, you're open to the salt water. And so taking stealth to sea was one of our biggest challenges. We had to go to a whole different concept, basically bake the stealth into the airplane. The main difference in technology that happened over the 10 years between an F-22 and an F-35 is we went to advanced curved composite structure. So the entire airplane outer skin of the F-35 is made of composites. If you look at an F-22 or earlier airplanes that were made out of metal, with composites we can put the actual stealth characteristics into the composites, and all you do is do the normal rain erosion and the normal type of paint scheme with some exceptions in certain areas to make the airplane stealthy. It's probably the biggest technical breakthrough on the program, happened in about 2004, is to get to the point where we could do that. There's two ships. The next two pictures are ships. This is the Queen Elizabeth II, the UK ship. What's unique about this is my BAE Systems deputy left the F-35 program to take over building the ship. And this ship was built from the beginning to be an F-35 aircraft carrier. So it has many of the same systems in it that the F-35 needs to communicate with. Those same systems are being retrofitted back onto other carriers as we go. You can see the ski jump there. The first deployment of the Queen Elizabeth II had 2 squadrons of U.S. Marine Corps F-35Bs and 1 squadron of UK F-35Bs. And the reason for that was the UK hadn't taken delivery of enough airplanes to man their whole air wing yet. They deployed to Syria, had a combat operational tour there. On their way back through the Mediterranean, the Italians flew their F-35Bs out, landed on the ship. And on a single day in the Mediterranean, they had 3 nations flying F-35Bs off of this ship, which is another testimony to the interoperability of the airplane. The other picture of the ship on the next slide is the Cavour. That's the Italian ship. Again, the Italians are buying both the A and the B and manufacturing both of those in their facility. This was already in existence, and so it had to be modified to handle the F-35B. But those are the 3 major operators of the F-35B at sea are the UK, Italy, and the U.S. Marine Corps. The next one is Nunn-McCurdy, and that was an event that happened as a result of the Weapons System Acquisition Reform Act in our Congress in 2009. They required that each of the programs go to the government estimate as opposed to the program estimate on completion. That was for budgeting realities, I guess. About 35 different programs exceeded their threshold, F-35 being just one of those 35, but it was the only one that you probably heard about, and that was driven by the pure size of the program. So it required recertification that the program was on track and would be completed, and there was a technical baseline review by independent experts, including Australian experts like Adrian and Betsy, that came in and did a full analysis of the program. And I'll turn it back to Adrian now to cover that piece.
Nunn-McCurdy was whereabout I became involved. The government in Australia at the time, Stephen Smith from WA was the Defence Minister. They got a bit concerned that we were going to end up with a delay and a capability gap between retiring our F-18s and F-111s and the F-35. So I was tasked to take a team and do an independent analysis of the program and in the United States and report back to my leaders in defence. We did that. I did that with Betsy Clark, my colleague, and some other specialists, and we concluded that the program was progressing quite well, really. The fact that the breach had occurred was more a technicality than it was a problem, and so we reported back, and we're the first independent team, we believe, to say that the F-35 is going to be successful. Everybody around the world was giving it a bad rap, mainly because they were misinformed. It's highly classified and there's a lot of information that we can't argue with because we can't say anything. And so the team, we did the review, came back, reported it was going to be successful. That was ultimately, I guess, accepted, and we did order the 72 aircraft eventually. I did end up doing 9 reviews over a 5-year period where we went back again multiple times, and every time we went back, Lockheed, yes, they had problems, and yes, there were things to be corrected, but they were doing it, and they knew the problems, they knew how to fix them, and it's been successful. And if you talk to any F-35 pilot today, they don't want to go back and fly anything else than the F-35. This is just one of the teams there. I was with Air Vice Marshal Colthorne, the head of aerospace acquisition. Betsy and I are the second from the back on the left, and Betsy is the only woman there. That was down at Fort Myers with the Marines in Florida. I think it was whammed by cyclones in the last couple of months. This is the rig. Tom said they did structural testing, and you can see there's an F-35 in the green up there where they shake it with vibrating actuators at 4 times its life. Tom said the life's about 8,000 hours, so they did the equivalent of about 32,000 hours of structural testing, and they would have discovered some issues, and then they can correct those, redesign any structural parts that were at fault. I'd never heard of any major problems coming out of that the aircraft passed those tests. It's a big rig, and all those bars and orange actuators you can see are vibrating, simulating landings and taking off, etc. This is a trolley built by Moran in Melbourne. It's got thousands of parts in it. It allows a single man to do an engine change on a carrier in Sea State 4C. They're worth about $2 million each. That was designed here by Moran, and Tom was very complimentary about their capability in terms of their automation. In fact, I think, Tom, you invited them back to also assist in setting up your production line.
Yeah, that's correct. They were coming off of the exodus of the automobile industry in Australia from a manufacturing standpoint, and F-35 allowed them to convert their operations in many ways to do F-35 work. So Moran has since acquired, I think, a couple of the other smaller companies that were part of the initial outlay of the supply chain, and they're doing great today. Their CEO, Rowan Stocker, comes through the U.S. every now and then. I get to see him, and I think they're probably one of the best suppliers we have on the program.
And there's another company in Brisbane called Farah. They've also been doing very well, and both of those industries are now well embedded into the aviation world and selling their technology through to commercial airlines, etc. as well, manufacturers. I know when I left Defence a couple of years ago, they built about 100 of these at that point in time, $2 million each. Tom, do you want to mention these people? We don't want to go through them one by one, but these are the chiefs of Air Force that were involved, and my boss, Dr. Stephen Gumley, and the Defence Material Organisation that were involved with the acquisition. But Tom, you might want to mention.
Yeah, they were all very, very critical to the program, especially Sir Angus Houston in the early days, and John Harvey were the two guys that we worked with very extensively in the very beginning, and as well as Dr. Gumley, and the rest of them throughout the period of time that we were doing the project. So just wanted to tip of the hat to those folks who worked so hard with us on the project.
The lady there is Catherine Roberts. I've worked for her a couple of times on other programs. She was a very brilliant engineer, became an Air Vice Marshal in the Air Force, and became the first space commander of the Australian defence programs in this country. So she was the leader, the first space commander in the Royal Australian Air Force. She's retired now as well. Tom, you might want to comment here.
This is a Secretary of Defence, Gordon England, who in a previous life was actually the head of the facility in Fort Worth when it belonged to General Dynamics. And Condoleezza Rice, Secretary of State, and then Brendan Nelson, who was the Minister of Defence in Australia, signing on for the next production phase of the program back in the day. Probably there's a lot of dates on here, but probably the last one is one that's worth looking at, is that more than 70 Australian companies have been involved in the project, and you can see the economic value and the number of jobs, things like that. So I think my early days going to Australia, I spent a lot more time with the Ministry of Industry and Defence than I did with Industry and Tourism than I did with the Minister of Defence.
It's worth mentioning production is continuing, and we're expected to go well into the 2050s. So that money that's coming into our Australian companies will continue as long as they continue to win the contracts for the parts they're doing, and $4 billion is a lot of money. And I think we paid $16 billion for the 72, so we might get that back into our economy. Tom, you can go with this, the Avalon Air Show.
Yeah, we flew a couple airplanes down for the Avalon Air Show. This is back in 2017, and I think they did a bit of touring around the country, and but it was the first time the airplane was on Australian soil, and I think it was a great move to do that. The next chart basically says, okay, what's happened since then? If you look at just a quick run through these charts, we're now, the F-35 is now replacing, hasn't done it completely, the F-16 as a standard in NATO. F-16s are going to Ukraine now, and part of that I think is to get their Air Force up to speed, and eventually Ukraine may become part of NATO. I don't know how that's going to work out. The F-35I, the Israeli jet, sometimes it's called the fourth version of the airplane. It's an F-35A, but it's got some special electronics that they fly and fight in a part of the world that has every air defense system you can think about, so they have to have a much more sophisticated capability. And then TR3 is Technology Refresh 3. You can see the little quote there. It's bringing in the new generation of weapons and systems as they come in. Well, I think all the F-35s eventually will be updated to that configuration. But then we talked about leveraging the airplane as a unified allied force now. We'll talk more about that in just a second. The next chart is just, again, is how the airplane is going to be upgraded. They're all being upgraded at the same time. All of the international partners are part of the process of defining those requirements. They'll be done with a series of software drops that bring the airplane up to another level of capability as we go forward. 2025 is the date that they're expected to have full combat capability. We go to the next one, and I'll just spend a minute on this one. If you look at what's changing in the world, this is one that's titled An Unstable Archipelago. If you look at all the countries around the Arctic Circle since the invasion of Ukraine, all those countries are now on the F-35 program, with the exception of Russia, obviously. But the U.S., Canada, the original partners, they were down in the Western Europe, and then the Northern Europeans. If you look at the other part of the world, it's the Pacific where you are, and basically Japan, Korea, Singapore, Australia will all be F-35 capable, as well as the U.S. carrier fleet that operates down in that part of the world. So in fact, the F-35 has brought in a coalition capability in both of those regions, which are the areas that are most unstable at the moment. So part of the promise of the project. The next one was just a quick shot. One of the objectives I had as a human was, since I was doing all this work with all the international partners, was to fly all their airplanes. And I got a chance to do that. I think I may be the only one that can say that, because I got to fly in the F-111 out of Amberley when I was in Australia before it was retired. There are no Air Force pilots that are old enough to have flown the F-111 because it went out of service in the U.S. about 20 years ago. So that was that. I think we can turn it over to questions now, Adrian, if you'd like.
Yeah, so that sort of quickly ends the program. I'm sorry to keep rushing a bit, but I've got to catch a red eye to Sydney tonight, so